Greetings and welcome to another installment of Easy SPSS. I'm Dr. Gross, and today we will explore the MANOVA, or the multivariate analysis of variance. And this is going to test whether group differences on multiple dependent variables are statistically significant when all considered together at the same time. And so today we'll look at exercise level and um, it, how it affects these three variables, these dependent variables. And we'll analyze these outcomes simultaneously instead of running multiple ANOVAs for each of them. And that's going to increase the sensitivity and decrease the likelihood of error. Put another way, the MANOVA allows us to test the effect of exercise level on multiple outcomes, height, weight, and age, at the same time. And ANOVA would test one of those at a time. So the MANOVA handles it all at once. And again, that's time saving, but it's also reducing the risk of error. So it also accounts for, how are those outcomes related to one another, which the ANOVA doesn't do. So more efficient than using multiple t-tests. It reveals more. And then again, better than multiple ANOVAs for the reasons that we just talked about. So let's go ahead and open the data set. I have an untitled, so I'm going to click my open. And this is not where I saved it. Here it is. So here's my data set, and you should have a similar data set from previous videos. But in data view, I can't get this thing to go down. There it goes. In data view, much like a spreadsheet, I can see all of my cases and all of my variables. The columns are representative of the variables like height and weight, and the rows, again, are representative of individual cases. So we have 32 cases. Let's account for some missing cases now that we're getting into some upper level analyses. So let's account for these four missing cells. And I'm going to type in a code that's generally recognized as a missing code. And this is for height and weight. That's where those were missing. So when I go over to variable view, which gives us a good excuse to talk about this real quick, each of these are our variables. Each row represents a different variable that we have, and then each column represents a property of that variable. Some labels that we've already done, and some values. Now we haven't done anything for missing. So height and weight were our variables where we have some missing data. So let's select height. I'm gonna go over to missing, and I will tell SPSS, but I clicked those three dots, the ellipses. Let me go back right there. I'm going to tell SPSS that a discrete missing value is represented by -99. So I'm going to do that for height, and then I'm going to do that for weight. So now, instead of doing something weird with that data or interpreting it weirdly, now it will say, oh, okay, this is missing data, so we will not include it in the analysis. So before we run the MANOVA, we need to check some assumptions. Now we can check some of these before we run the analysis, those that I've highlighted right there in green. And then some of them we can check because it's automatically provided in the MANOVA output. So let's do this one first, since we can beforehand. And we'll check the assumption of linearity. And what that means is that each pair of dependent variables has a somewhat linear relationship with each other. And we can do that by creating scatter plots of, for example, height versus weight, but we want to compare all of them against each other. And what we're looking for is a roughly straight line. And if we can see that, then we can assume that linearity is met, or that assumption of linearity has been met. So let's do it. And I'm going to do the first one slow, but then I'll generate the other two rather quickly, and then we can discuss it. So I'm going to go to graphs and then scatter dot. Graphs, scatter dot. It auto selects simple scatter, which we want. And then we're going to define its properties. So I'm going to switch. I right clicked and I'm clicking variable, and it just makes it easier for me. So I want to create scatter plots for all of my all of my possible combinations of dependent variables. So I'm going to select height, move it to the Y. I'm going to select weight and move it to the X. And then I'm going to click OK. And it's going to generate a plot for us. But I don't want to look at it right now. I'm going to do the other two real quick. Again, graphs, scatter dot. We're going to define. So we compared these two, but let's compare now height and age. Again, it'll generate some output, and then I'm going to do it one more time. So let's compare weight and age. And so looking at these few combos, again, I'm looking for a roughly straight line. And for height and years, age, it's, you know, it's definitely got some points that don't trend, but roughly I can kind of see maybe a positive trend in the relationship. And likely, at a certain point in time, you're going to start growing taller as you age. And at a certain time, you'll stop, obviously. But again, we have a very small sample size of, roughly middle-aged range of individuals. So roughly a straight line. And then if we look at weight versus age, so we did height versus age, and there's weight versus age. Yeah, definitely a more pattern there, representing a straight line. And then I think I skipped over. There's height and weight. So again, roughly a straight line. So we can say that linearity, according to these scattered dots, that assumption has been met. We'll revisit these when we run the output. But there are two more that we can look at. Normality, again, we're checking for normality. Normality of the residuals. And so we can do this in the explore function, and we can also kind of do this part in the explore function, and I will talk to you about that as I go. So let's go to, this is our output screen, which you can go straight to these things from your output screen. But let's go back to our data view, and neat little trick if you forgot value labels. Right, I can see my code changes, and I can see my or I can see my codes, and then I can see my descriptions for those codes. So we'll go to Analyze Descriptives Explore. And when the dialog box opens, we want to, again, I'm going to change this. I right-clicked. Okay. I'm going to change this, and height is selected. I can move those over, individually, or I can just select, hit Control, hold it, select all of them, and move them over. And so I want to just move those three to my dependent list. And then I'm going to click a couple of things here. So you can get your descriptives, which a little bit is talked about down here, straight from the Explore dialog box. I don't want to say options because that says options, but these over here, I have a statistics tab that I can press, and it will give me descriptives, and it will check for outliers. I'll hit continue. Now back up here, we do want to click plots and then normality plots with tests. And this is going to allow us to look at some normal QQ plots. And the descriptives will allow us to look at skewness and kurtosis. And so we're just trying to check and see among all of these tests, is the data normally distributed? And we need that assumption to be met because we are running a parametric test, a MANOVA. So plots. I'm going to uncheck stem and leaf, and I'm going to check histogram. I'm going to check normality plots with tests. Click continue. Nothing there. Now we need that. So down here, I talk about checking box plots to make sure that there are no outliers. And I'm telling you about how to interpret those box plots and what they actually represent. But SPSS automatically generates those box plots. So kind of a redundancy down here, but let's look at these output data and let's look for normality and the absence of outliers. So first, let's look at our case processing. We had some missing variables that we put in, two cases that had some missing data. So those cases were not included. And valid number of cases was 30 out of the 32 cases. So it used 30 cases and ignored those cases where we had missing data. So our descriptors, real quick, I just want to look at skewness and kurtosis because I'm interested in normality. And as long as it's not less than 2, or the absolute values, as long as it's falling within a less than 2 or greater than -2 range, we can support normality in that way. So skewness, I'm just looking to see, is it less than -2 or is it greater than 2? So for inches, no. For weight, no, but we're kind of close. Perhaps a little kurtotic, we'll see. And then age, again, within an acceptable range of skewness and kurtosis. Now, as we continue, here are our tests of normality. Shapiro-Wilt was, and we're looking for non-significance here. So is it less than 0.05? No. Yes. No. So for height and age, normality assumption has been met. So we're safe. For weight, though, it's questionable, isn't it? It's less than 0.05, which might indicate a non-normal distribution. However, the KS, it's tough for me to say, the KS test was non-significant. So let's just proceed with caution. Again, we can use this along with the skewness and kurtosis values to say that, well, even though weight may be questionable, if we look at the skewness and kurtosis values for weight, it's below that negative, it's within that range of -2 to +2. So we're okay. All right, so we can support normality. Now let's look at the QQ plots. And what we're looking for there is roughly a straight line or a straight diagonal line. So let's look at here's our histogram. But let's look at our normal QQ plot for height. Yes, it trends around that diagonal. Here is our box plot for, I believe it's for height. Yep. Yep. Could also look there. Nothing outside of the whiskers, so no data points falling outside, which indicates no extreme values, no outliers. Histogram for weight. Here's the normal QQ plot for weight, and yes, it does differ a little bit more than the other, but still kind of trending. It's got some variation, but it's still kind of roughly following that line. And then no extreme values for weight that would lie outside of these whiskers. Histogram for age. Very good normal QQ plot. Very representative of a bell curve, so no outliers. All right, so what does that all mean together? Well, with the normal QQ following roughly on a straight line, with the skewness and kurtosis values within that range, even with a slight deviation in the normality test, the Shapiro-Wilks for weight, even with that, we can say that the assumption of normality is supported, considering all of those things together. That was a lot. So let's go ahead and we will check these other assumptions, homogeneity of covariance and the homogeneity of variance. But we can do that while we do the MANOVA. So let's go ahead and run the test. All right. So the data is loaded, and we'll go to Analyze General Linear Multivariate. So Analyze General Linear Multivariate. And we're going to set up the model in this dialog box. So we're going to move height, weight, and age to the dependent variables box. Right click, display variable names. That makes it easier. So I'm going to move my dependent variables, height, weight, and age, to the dependent variables box. Height, I'm going to hold down control. Weight, age, I can release control. And then I'm going to click dependent, and we'll all go over. Now, we want to move exercise level now into the fixed factors box. So here's exercise level. Still didn't fix that. I'll move that over. And now we'll go to some options. We can, well, first let's click. I'm gonna go from top to bottom, and I'll kind of jump around here. So for plots, nope, don't want those. For post hocs, I do want to see if there is a significant main effect. I want to see where exactly are those differences? Where are those significant differences? Where do they lie? So for that, we'll need a post hoc, and I want to check. I just double clicked. Between which exercise levels is there a significant difference based on our dependent variables? And so for post hocs, I want the Tukey and the Bonferroni for pairwise comparisons, and I'll describe what those are when we get there. So I'm going to click those two and continue. Then I want to go to options, and I want my descriptive statistics. I would like to know how much each of those variables or all the variables influence the independent variable. So that's your effect size. I want homogeneity tests, and that will be Box's and Levine's tests. And I would also like to assess normality and homoscedasticity. So I can do that by checking this residuals plots. And I'll talk to you about what that output means. Okay, so let's go ahead and run the analysis. All right, and so here is our general linear model. And that's right here. And everything that we did prior to this general linear model is up here. So if I wanted to quickly go to my scatter of weight, I could come over here and just click, and it'll take me right there. But we're down here. So let's go back to the general linear model and discuss the output. Okay. So I'm going to kind of jump around here too. I apologize, but we'll look at a lot of output. We'll look at the multivariate tests, the descriptives. We will look at boxes and Levines to see if we have satisfied those assumptions. If we get a significant multivariate effect, then we'll look at our post-hoc tests to see where those differences lie. And then our residuals will give us, along with the output that we explored earlier with the normal QQ plots and the skewness and kurtosis, those values, the skewness and kurtosis, will pop up again because we asked for some descriptives. So I'm going to jump around a little bit with all this, but I'll try to bring it all together and make it understandable. So first, let's look at our let's first look at the assumptions and see if the model that we ran can be done. So let's look at boxes test first. That's right under here, under the general linear model. Here's boxes test, and it's not significant, 0.497. So the covariance is equal across groups. So we can say the assumption is met. We're safe. Let's look at Levine's tests for equality of error variances. So again, we are looking for a non-significant test. If it's significant, that means that we might have violated an assumption. And for weight, we know that that's questionable. So let's talk about it. For height, a value of 0.398, well above 0.05. The assumption is met for height. For age, 0.951, we're good. And for weight, 0.089. And so, again, safe there, 0.08. Now, we looked at our normal QQ plots earlier and noted that they were roughly a straight line, that skewness and kurtosis were within acceptable ranges or an acceptable range. And if we look at our residual plots, what we're looking for is a random dispersion, and we can support normality and homoscedasticity. If we look at the standard residual versus the observed, it's further supportive of normality for these variables. Okay, so all assumptions considered, we've met a grand majority of them. Weight is questionable, though with a small sample size, it can be very sensitive. So considering all of those things together, we can proceed and say that even though weight was questionable, the assumptions have been met. So let's now look at the descriptives, which is going to come first. We asked for descriptives, and so it's giving us the means, the standard deviations, and then the number of cases that fell into those groups, right? So for exercise amount, our independent variable, the low group average height was 68.786. The average height for individuals that fell into the moderate category was 63.33. And the average height for individuals that fell into the high exercise category was 64.385 with those standard deviations respectively. And so how do you interpret that? Well, you would say individuals that were taller tended to be in the low exercise category. And individuals that were shorter tended to be in the moderate or high category. So let's go now. We've discussed this assumption. Let's go to the multivariate tests. So this output is going to show statistics like the Pelias trace, Wilks lambda, Roy's largest root, and usually we'll interpret Pelias trace or Wilks lambda, and we want to look at this right here. This is just saying, is it different from zero? We want to look at this line right here, exercise level for multivariate tests. And so all p-values for exercise level are less than 0.001. So significant at the less than 0.001 level, meaning that exercise level significantly affects the combination of height, weight, and age, our dependent variables. And so if we follow exercise level across, the Pelias trace value is 1. F value is 8.839, but we're looking over here the significance. So yes, significant at that level, and Wilks lambda also significant at that level. Now, partial eta squared is how much does it account for? How much variance does it account for? Well, you can say that exercise level, depending on our variables, height, weight, and age, explain roughly 50%, 65% of the explain the data, 50% of the data, right? Or 50% of the cases, depending on our dependent variables. And so height, weight, and age account for 50% of the reasons why people might fall into these exercise categories of low, medium, and high. So I know that was kind of all over the place in its description. Just rewind it and listen to that last part. I think that made the most sense. So our multivariate model yielded a significant result. So it's saying that, yes, these dependent variables have an effect on what kind of exercise level people or exercise level program people might fall into, low, medium, or high. So, but it doesn't tell us anything other than that. So now we would like to run some post hoc tests to see, all right, well, where do those differences lie? Assumptions, check. So let's look at the tests of between subject effects. And we want to look at, now the corrected model says, all right, considering all these together, what was the overall significance? But I want to look at right here, exercise level. So height and weight are both significantly affected by exercise level with a p-value at this level or p-value less than that level. So where do I see that for height and weight? For exercise level, height, a p-value of less than 0.001. Weight, also less than 0.001. And even age, less than 0.001. Scrolling over a little bit further. So our partial eta squares, again, height accounts for 60% of the variance in why people might be categorically represented in certain exercise groups. Weight accounts for a very large amount of variance, and age the least. Now, so this is saying that separately, height significantly affects the exercise level group that one might fall into. It is also saying that weight by itself, right, is also significant. So what's happening here is basically you've taken this multivariate test that tests all of them at the same time, and now you're running multiple ANOVAs to see, okay, well, if I ran it one at a time, would they still be significant? Would the model still be significant? And here you're saying yes, that together considered, they are significant, and separately now, they are significant, or significant, statistically significant in in the differences between groups. So now we look at our pairwise comparisons, our multiple comparisons. And this at face value might seem, difficult to look at, but all it's saying is, all right, well, where exactly are the significant differences? And so if we look at this, for height, here are our exercise amounts in these columns, right? And so it's comparing exercise groups for the dependent variable height. And so for height in inches, according to Tukey and this other test, Bonferroni, that we ran, these are our post hocs. For height in inches, when comparing the low to moderate exercise level groups, there is a significant difference. When comparing low to high exercise groups, there is a significant difference. When comparing moderate to low, there is a significant difference. However, when comparing moderate to high exercise level groups, there is not a significant difference. And so what you could infer about that is, for weight, so I described height, but let's look at weight real quick. So weight for those in the low and moderate categories for exercise level, there is a significant difference in their average weights or their mean weights. For the low to high exercise group, there is a significant difference. So from low to high, there's a significant difference in the average weight of individuals who fall into those categories. Now, for moderate to low, significantly different in the weight, but for moderate to high, it is significant, but it is below 0.05. However, I might interpret that cautiously. Now, according to Bonferroni, it is not significant, the moderate to high. So again, I would really interpret that with caution. So overall, the pairwise comparisons or post hocs indicate that for weight, the low group significantly differs from both the moderate and the high groups, while the moderate and high groups do not differ significantly from each other. And again, you can see that, and I don't know why it's incorrectly written. All right, so if the p-value is greater than 0.05, they do not differ significantly. And again, we can see that the moderate and high groups don't really differ that significantly from each other. The low to moderate groups, again, for height, low to moderate, significant, low to high, significant, moderate to low, significant, but moderate to high, not significant. And for weight, again, similarly, the moderate to high group is questionable as far as significance. Now that's for Tukey. For Bonferroni, the moderate to high group is definitely above 0.05, 0.054. And then finally, if we went down to age, the low to moderate groups do not differ significantly. The low to high groups do. So that you might say high intensity or high volume exercise compared to low intensity or volume of exercise, there's an age difference that's meaningful. And I would agree, as I've gotten older, it's dropping. It's gone down a little bit. So that makes sense as far as the post hoc goes, at least in my experience. So we won't necessarily worry about these homogeneous subsets, but I did want to end with a final takeaway and then also an example that might make more sense for a MANOVA. I didn't want to force you to use a completely different data set. So our overall findings is that the MANOVA, the model, confirms that exercise levels significantly affects our dependent variables when all considered together. We do this because it's better than running them all individually, because that and then trying to compare, because that can inflate the error. And so by doing it all at the same time, we have an error reduction. And our assumptions were, I'd say 99% met. We did have an issue with weight, but we looked at a lot of things together. And considering all of those things, we can support the assumption of normality, but there's slight caution for weight. Our post hocs, so our MANOVA, we found that it was significant, and so now we wanted to know, well, where do those differences lie exactly? And that was our post hoc tests, which showed that there were group differences, right? Significant group differences, particularly for weight, where the low group significantly differed from the other groups. And I would say also age significantly differed definitely from the low to high group. Imagine that a district is evaluating teaching methods, right, at method A, B, or C. And instead of running separate ANOVAs, the MANOVA would allow the district to assess both outcomes, math and reading, together simultaneously. And that would reduce error by accounting for the interrelationship between math and reading scores. Perhaps those are related somewhat. And this helps us to make certain that differences are due to the actual teaching method rather than some random variation or chance or pre-existing differences among students. So that would be an application of the MANOVA in an educational setting. All right, well, next is the MANCOVA in our series of videos where we will account for age as a covariate, which will be interesting. Tune in for that next time. I'm Dr. Gross, signing out.